All right, this is the rest of section 5.1. We're looking at operations with functions. We've looked at adding, subtracting, multiplying, and dividing. I mentioned that there's a fifth operation that is pretty important, and that's called function composition. So here's a definition. It says, let f and g be functions. The composite function, which is denoted by the way that we read this is to say f composed g, is defined by f composed g of x equals f of g of x. Okay, so basically with function composition, you are plugging one function into another. Okay, whatever function is written after the open circle there, you're going to be plugging into the one that is before the open circle. So g is being inserted into f, not the other way around. There is an order to what we're doing here with the notation. Okay, so here's an example. Suppose I have these functions f of x and g of x, and I want to compute the composite function. F composed g of x means that I'm going to plug g into f. So g of x is given, that is 2x plus 1, which means that everywhere that I see an x in f, there's a couple of them, I need to replace those with 2x plus 1. Okay, so I've replaced the x's there with 2x plus 1, and then I need to simplify. So 2x plus 1 times 2x plus 1 would be 4x squared plus 4x plus 1, and I'm also distributing the negative 3 into these other two terms. When you collect your like terms, you end up getting 4x squared minus 2x minus 2 then as the answer. Like any other function, we have input values and output values. So like if I want to plug 3 into the composite function, I can actually handle the calculation a couple of different ways. I could do it the same as I did when it was x. So I would need to compute f of g of 3. G of 3 would be 7. So essentially this problem here is just asking us to find f of 7. Here's f of x, so when I let x be 7, 7 squared is 49. I'm subtracting 21 from 49, that'll give me 28 as the answer. Another way that you could have done the calculation is you could have used the formula that we've created over here, and you could have plugged in 3 in for x in this form. So if x is 3, 3 squared is 9, times 4 is 36, minus 6 is 30, minus 2 is 28. Okay, so either way you're going to get 28. Now, probably in general it would make the most sense to use the formula that you've created if you've done that previously in the problem. Otherwise, why are you finding this formula if you're not going to use it for anything, But either way, you'd still get the same number there. Now, we need to not get this confused with another operation that we've talked about, which is the product function. Students sometimes want to do that. They see this open circle here, and for whatever strange reason, they think that they need to multiply. Don't do that. Okay, f times g of x means I'm multiplying these two functions, and I've done that calculation here with these two functions that were given. When I FOIL out these expressions, I end up getting a result that is totally different from what we had circled up here. Well, that shouldn't surprise us because we're doing two totally different things, right? I mean, in one case, I'm plugging a function into another function, and in another case, I'm multiplying functions. Totally different operations. Okay, so don't make that mistake. These are different from each other. Now, one example that I like to give for understanding function composition, and I'll talk about some others here in shortly, but the output values from one function are the new input values for another function. A car wash example is is an example that I usually use in class. Suppose that it costs $5 to get your car washed, okay? And the car wash machine only takes quarters, let's say. All right, now suppose that you only have a $5 bill. Are you going to try to fold up the $5 bill and shove it in the car wash machine? No, not unless you want to lose your money, right? You have to first go get a bunch of quarters. So the output values from the change machine would be the new input values into the car wash machine. Okay, that would be an example of what we mean by function composition. Okay. Now, I mentioned that there is an order to how we are writing the functions. So, like, suppose I wanted to compute g composed f of x. Well, since f is coming after the open circle, that would mean that I'm going to plug f into g. F of x is given here. So everywhere that I see an x in g, there's only one. I'm going to replace that x with x squared minus 3x. I've done that, and when I simplify, I end up getting 2x squared minus 6x plus 1. Notice how these two expressions are different from each other. That shouldn't surprise us, right? So we're plugging, g into f rather than f into g. Now, sometimes f composed g and g composed f will actually end up being the same thing. It didn't happen here, but we'll see that later on. When that happens, that's special because f and g are called inverses of each other, and the next section is all about inverse functions. Okay, I'll talk about that in the next video. Now, there are lots of different real-life applications of function composition. Conversions are really kind of the application, I would say. So I've got a couple of examples here. Suppose that I wanted to know how many inches are in a mile. Well, I don't know that off the top of my head. Okay, but if I were to know how many inches are in a foot and how many feet are in a mile, I could figure out how many inches are in a mile. That is function composition. You're taking the output values from one function and they're the new input values into another function. Suppose I wanted to know how many cups are in a gallon. I don't know. I don't bake. And so I don't know that off the top of my head. Okay, but if I did know how many cups are in a quart and how many quarts are in a gallon, I could figure out how many cups are in a gallon. Okay, again, that's function composition. Scientists sometimes have to work with temperatures where the units are different units. The common unit measures for temperatures are degrees Fahrenheit, degrees Celsius, and then kelvins is a common one for different areas of science. And so suppose that you had a temperature value that was given in degrees Fahrenheit and you wanted to know what that looked like in kelvins. Well, there is a formula that would allow you to convert that number in degrees Fahrenheit to degrees Celsius, and there's another formula that would allow you to convert a number that is in degrees Celsius to kelvins. So you could be able to figure out what that temperature is in degrees Fahrenheit in kelvins, but that's exactly function composition. Okay, so there's several real-life applications of what we're doing here. Conversions, like I said, is pretty much the application. Below that, I've got the information for how to find the domain of the composite function. There's a list of 3 steps. The first thing that you're going to do is find the domain of g, because g is being inserted into f, and so we need to know what we can plug into g first before we plug in these numbers into f composed g. Step 2 is you're going to compute the composite function and simplify. Simplify as far as you can go, and then once you're in complete simplified form, determine the values for x. And then step 3 says that the domain of the composite function will be the answers from both steps 1 and 2. Here's an example. Okay, suppose that we have these functions f and g. I want to do a couple of things here. with these functions, the first thing that I'd like us to do is compute the composite function f composed g of x, and then we'll state the domain. F composed g of x, by definition, means that you're going to plug g into f. So here's g of x. Everywhere that I see an x in f, there's only 1. I'm going to replace that with 4 over x minus 1. So I've done that, and now I begin to simplify. And okay, I'm going to leave the 1 alone up top. In the denominator, I'll need to get my common denominator here. 2 is the same as 2 over 1. And so with this term, I'm multiplying the top and bottom by x minus 1 so that I've got the common denominator. That way I can keep the denominator and add the numerators to get a single fraction there. When I do that, 4 plus 2x minus 2, be sure that you distribute. 4 minus 2 is 2, and then I've got the 2x still. So 2x plus 2 would be the numerator part. Now, the last thing, since I'm dividing by a fraction, I would flip the denominator and multiply. X minus 1 over 2x plus 2 would be the answer in simplified form. Now, if I wanted to know the domain of the composite function, according to the information that I had written here, I need to first get the domain of g. The domain of g is all real numbers except for 1. I know I can't divide by 0. And then step 2, I need to compute the composite function and simplify. Okay, I've already done that. And I need to determine the values for x. Well, it looks like x can't be negative 1 in this result because there's going to be a problem with division by 0. So all in all, I want to throw away 1 and negative 1 in stating the domain of f composed g. Suppose I wanted to compute g composed f. Well, that would mean that I would plug f into g. Okay, now f of x is given here, so everywhere that I see an x in g, there's only 1. I'm going to replace that x with 1 over x plus 2. I've done that, and then I just begin the process of simplifying this. 1 is the same as x plus 2 over x plus 2, and that's how I'd want to look at that because now I've got my common denominator here. So I can keep the denominator and add the numerators. 1 minus x minus 2. 1 minus 2 is negative 1. And I've still got the minus x there. So I've got my single fraction. Okay, now 4, that's same as 4 over 1. And again, since I'm dividing by a fraction, the rule would be to flip the denominator and multiply. So 4 times x plus 2 would be 4x plus 8. Negative x minus 1 would be in the denominator. And this here would be in complete simplified form. If we wanted to know the domain of g composed f, we would have to first know the domain of f, since f is being inserted into g. And of course, you can't use negative 2 for f of x. That's a problem with division by 0. And then the next thing is we'd want to compute the composite function and simplify. Okay, we've done that. In this result here, we don't want x to be negative 1. So all in all, the domain of the composite function would be all real numbers except for negative 2 and negative 1 from what we had here. All right, the next thing is, so you could find f composed f of x. That would mean that you're just going to simply plug f into itself. F of x is 1 over x plus 2. So everywhere that I see an x in f, there's only 1. I'm going to replace that with 1 over x plus 2. I've done that, and then I want to simplify. 2 is the same as 2 over 1. And so I'm going to multiply the top and bottom by x plus 2. That way I've got my common denominator there. And I can keep the denominator and add the numerators. I'm leaving the 1 alone up top. 1 plus 2x plus 4. Again, make sure that you distribute. 1 plus 4 is 5. And then I still got the 2x there. So I get 2x plus 5 over x plus 2 down under. And of course I'll want to flip that since I'm dividing by a fraction. And it looks like x plus 2 over 2x plus 5 would be my answer then in simplified form. If we wanted to find the domain of f composed f, of course the first thing would be to get the domain of f, which makes sense. We're only using f in the calculation. And the domain of f, we've already said earlier, was all real numbers except for negative 2. And with what I have circled here, of course, I don't want to divide by 0, so if you were to take 2x plus 5 and set that equal to 0, x would be equal to negative 5 halves, and of course that's what I don't want, since I can't divide by 0. All in all, we should be throwing away negative 2 and negative 5 halves then. Okay, and I can certainly compute like g composed g, that would mean plug g into itself, etc. Here's the homework problems in the book. Be sure to look at those problems, and we're now done with section 5.1.